And good evening, everybody. In this presentation, I will give you a brief overview of the activities we have carried out in the framework of a national funded project we carried out a couple of years ago with reference to the design and validation of a morphing high-leaf device that is based on shape memory alloys actuators. As I mentioned, the research project that represents the framework of this activity was funded by the Italian government and was a project involving three main entities: my university, Alenia Aermacchi, nowadays Leonardo Aircraft, that is the industrial partner of this project, and CIRA, that is the Italian Center for Aerospace Research. What we wanted to do in that project was to identify some different and unconventional strategies for wing morphing, aiming at proposing in perspective for future application, flyable alternative for classical hyperlift devices, mainly the flaps of the wing. We wanted, in few words, to replace the conventional flaps on the wing with morphing structure, so with structure that were able to change their shape according to some controls that were given by the pilot of the aircraft. Two different innovation streamlines were sticked out in this project: the morphing wing streamline, because of course you know that wings are not supposed to be morphing, so to change their shape under control of the pilot. And another innovation streamline was the smart material streamline, because we wanted to implement morphing structures by adopting actuators embedded into the structures based on new unconventional materials, and in the specific application we wanted to use shape memory alloys materials. Okay, this represents in a very rough sketch the domain of our research. This is a wing of the reference aircraft we selected. We are talking about an aircraft for civil aviation, for civil transportation, regional segments. So, namely, just to mention a kind of model ATR 42, for instance, with 90 passengers or 70 passengers. And we wanted to replace the conventional split flap of the wing with a morphing architecture. So with an architecture that not implemented the increment of lift by rotating the trailing edge, this part of the airfoil, but implement the same increment of high lift by morphing this part, so by cumbering this part of the airfoil, so the trailing edge. Here you see the dimensions that are pretty important of the region we wanted to investigate. And so, as you can imagine, since we are dealing with a civil transportation aircraft, the change of shape of the structure that was, of course, given by the actuators had to be robust enough in order to counteract the very important aerodynamic loads that are expected in service for this kind of architecture. So first of all, we had to identify the target morphed shape for our airfoil. This is how the flap works mainly in a conventional way. So the last part of the airfoil is deflected by an angle delta in order to have an increase of lift used for takeoff and landing. What we wanted to do is to avoid this rotation and to basically morph this region into another kind of airfoil, which has a different kind of camber with respect to the one of the baseline airfoil. So in order to find out the target morphed shape we had to do, we basically consider a different kind of deflection of the original airfoil, and so different kind of geometric configuration, each one related to a given deflection of the flap, indicated as FA delta. And we associate to each kind of this configuration a morphed configuration, here called as gamma of FA delta, in which basically we replace this part that is a classical deflection of the last segment of the airfoil with this part that is a cambered morphed airfoil, having the tip in the same position we have in the conventional solution, but the camber, that is this red line here, changed into a parabolic arc. In this way, we have an extra increase of lift, because from one side we have the effect due to the deflection of the tip, and on the other side we have the positive effect due to increment of camber in this area that gives an extra lift. For all the morphed configuration, we evaluated the distribution of pressure coefficient, and we evaluated also the lift coefficient for the wing. And since the target for takeoff and landing was set by the industrial partner to the value of 2 for alpha equal to 5 degrees, we find out the morphed shape given us this kind of CL max for the arc roll. And basically the morphed shape we obtain that we had to reproduce by our unconventional architecture was thus related to a deflection of delta of 12 degrees with a tip displacement of 160 millimeters. Having found the morphed shape we had to implement for our morphed airfoil, we evaluated also the relevant design loads that had to be counteracted while morphing, basically the loads that are due to the aerodynamic pressures in service. And we did this with reference to a slice of the flap, having a span of 300 millimeters. That was also the region we selected for making our physical demonstration of the concept we wanted to implement. How we decided to actually allow the transition of the structure from one baseline shape to the morphed shape. Basically, we substituted the classical rib of the aeronautical structures with a segmented rib in a finger-like fashion. The rib is not a unique plate. This is the part of the trailing edge we have to morph. It's not a unique plate as usually done in aeronautics, but it's a join up of 3 different blocks that are hinged to each other along the camber line of the airfoil. Moreover, there are some cross links that you see here in black that connects blocks that are not adjacent to each other. So the block B2 is connected to the rear spar of the wing. The block B3 is connected to block B1. In this way, these 3 blocks represent a single degree of freedom mechanism in the sense that if you move just one of these blocks, all the other follow the movement like the pieces of the finger of your hand, according to specific gear ratio around these hinges that are a function of the position of these crosslinks. With an inverse kinematic problem solution, we found out the position of this crosslink in order to allow the transition of this configuration to the target morphed configuration upon the actuation of the first block. This actuation was carried out by means of an actuator that is represented schematically here, based on a SMA alloy. This actuator is an arch spring with an SMA installed on it. That is the active element of the arch spring. Let's have a look on this actuator. We have a titanium spring here and an SMA ribbon that is installed on this titanium spring. By heating this this element in SMA, basically we use nitinol for this application. We were able to implement the shape memory effect, and this material was able to contract by 3%, okay? While contracting by 3%, it generates a relative movement between this part and this part. Since this arch is constrained on one side on the movable block and one side on the other block, this contraction here generated the rotation of this part with respect to the rear spar and automatically all the other parts because this is a mechanism. Why we have this arrangement? Because the SMA we used was a one-way SMA material, so that when you activate the material, you basically realize the transition from martensite state to austenite state. It recovers its original shape, and so it contracts. But when you remove the heating, the material stays in that configuration, and you need an extra force that is, in this sense, given by the titanium spring that restretches again the SMA materials in order to have a cyclic activation. Clearly, the temperature at which we had to activate the SMA and the recoverable strain was found out after an iterative finite element-based analysis implementing for the SMA the model of Liang and Rogers for the prediction of the recoverable strain as function of the activation temperature and of the stress state of the material. Here you see the device we arrange and we test in laboratory. So the SMA is here, and this is what happened when you activate the SMA. So basically it contracts and the arch change its shape. Here you see just another picture of the element with, of course, here we have an endless queue that was just used for the installation of the SMA, because basically you compress this arch, then you install the SMA, and then you release it so that the SMA is already pre-stressed when you activate it, and then you activate the SMA and you have this cyclic activation condition and this cyclic change of shape of the arch. The arch was installed in the structure of the trailing edge in this way with this 2 amplification fork. As you see, this amplification fork is connected to the rest of the wing, this one to this block here. So when the SMA contracts and so make this part move together with this part, this moves with respect to this part, and so all the trailing edge change its shape. You have here the picture of the physical installation. From the experimental point of view, what we obtained was that basically upon the activation of the actuation based on SMA, that here it's inside this box of the trailing edge, we had the ability to reproduce exactly the transition from the target morphed, the target nominal shape to the target cambered morphed shape, realizing the final tip displacement we wanted to realize of nearly 60 centimeters with a power supply of 5 watt that is totally compatible with the available power you have on the aircraft, and with an activation time of 50 seconds that is fully compliant with the activation time you need for implementing an hypothetical change of shape for takeoff and landing phases. So as conclusion, the proposed specifications were met for the specific application. The architecture proved to assure large deformation capabilities while withstanding external loads. And so this is also an important result for the specific material we have used. The actuator structure interface were optimized with respect to established performance in terms also of geometric features. And the setup procedure proved effective in predicting the equilibrium point between the structural assay behavior and the SMA actuator. Moreover, the SMA resulted pretty efficient as a tool to actuate our morphing structure for this specific aeronautical application. All this thing that I have showed you, so both the architecture and the SMA actuators, were then also proposed as idea for a patent that was obtained. So there is here also the reference of US patent. You can consult if you want more detail on the architecture you have seen. So thank you for your kind attention.